Okay, so today we have with us Blair Bilodeau, who will be talking to us about impossibility theorems for feature attribution. Blair is currently a member of research staff at the Volion Group, where he develops statistical models and techniques for investment strategies. And before this, he did his PhD at the University of Toronto with Dan Roy. He's received several awards, but most importantly, he worked on this problem while he was a research intern at Google Brain with Bean Kim. And yeah, with that, Blair, the floor is all yours.
Awesome. Thanks, Suraj. Thanks everyone for joining. I'm really happy to be here today. One disclaimer I have to make is this work is not affiliated with Volion at all. That's my day job, but this is I wrote this paper while I was an intern at Google, and Natasha, Pengwei, and Bean were all at Google at that time. So we wrote this a couple years ago, but it appeared in PNAS earlier this year, so it seemed like a nice time to share it again, kind of with the community, and especially in this seminar, which it seems kind of purpose-built for almost. At any time, it's a very small group, so feel free to just interrupt and ask questions. That's no problems. We can have kind of a discussion style if things get off track. Okay. So let me start with basically the framework that the paper works in and that we're going to be working in for this talk. And that is the kind of subset of interpretability of feature attribution. So the basic idea here is that I'm going to take as input a trained model, and I want to emphasize that the model is already trained, which means I'm going to use model as a synonym for function. It's just something that takes an input and gives me an output. And this means that it can be anything from a neural network, like an image classifier, to someone sitting at a desk deciding whether they're going to approve or reject a loan, right? It doesn't have to be an ML trained model. It can be anything that takes inputs and gives outputs. And what my feature attribution do is it takes in this model and it's going to assign a score or an attribution to each feature of the input. And so it's kind of important to realize that this has to do with the actual thing that my kind of model is taking as input. It has nothing to do with parameters of the model. So if my input is an image, then each feature might be a pixel of that image. So just some quick examples so we're all on the same page of what we're talking about. These are from some kind of canonical papers in the area, one on Shapley values, one on integrated gradients. And the most common way to visualize feature attribution is with these so-called saliency maps, which say basically take these scores and assign them to a color, and then you can produce a heat map for each of the features. So because these are explaining images, or the model is classifying images, each feature is a pixel. So on the left, we see this kind of heat map that corresponds to, reds and blues are somehow larger or smaller attribution scores for different pixels. And over here, it's an image of, I believe this is an eye. And so then they can like overlay this heat map that it corresponds to the attributions assigned to each pixel within the eye. And this is how they kind of explain what the model is doing for this specific input example. And it sometimes can be hard to pin down exactly how people want to use feature attributions, but I think that it's fairly safe to say that in the literature, a basic claim is that when a feature gets large attribution, this implies that the feature is important in kind of big scare quotes to the model in some sense. So, I mean, we could spend all day debating what it actually means for a feature to be important to the model. And instead, I'm going to kind of try and walk this back to something that I think is a fairly benign statement, but it's kind of an axiom in the sense that we can't prove or disprove this. This is just something that I believe to be true if we want to be doing kind of anything with feature attribution. And that's that if the attribution is near zero or the attribution is very large, this should imply something different. If this is not true, then it's kind of hard to say what feature attribution is useful for in some sense. Like what can we use it for if it doesn't imply anything different when the values are very different? And the main punchline of this paper is that for some very common methods, you can't conclude anything new about the model in a local sense, so around the example that you're trying to explain, if all that I tell you is either the attribution is 0 or the attribution is 1,000 here. This doesn't tell you anything new about what the model is doing locally. And so how can we interpret this in terms of actual implications in practice? Well, we can think of that, suppose that I tell you your feature attribution for this feature and this model at this example is basically near 0, or it's exactly 0. a kind of thing that you might want to then conclude from that is that the feature is not used by the model near X, near the example that I'm trying to explain. Or you might say, well, it's going to be hard for me to tell if the model really uses it. What does it even mean for a model to use a feature? Maybe I could at least say that F is insensitive to perturbations of this feature near X. It's not, changing the value of my F of X in a large way. And one could say that, a reasonable definition of unused is this. We could say that this implication is probably true, that if my model just totally ignores the feature, then it's going to be insensitive to perturbations in this feature. It was established very early on in the field that the reverse is false, because if you have, say, a ReLU where your model can saturate, then it's fairly easy to come up with a somewhat coherent definition of used, where kind of locally it's still going to be insensitive to perturbations. If you imagine that, kind of just tweaking the feature a little bit is not going to change the output. But if you tweak it sufficiently far, then your ReLU stops being saturated, and you could change the output pretty significantly. And the main kind of punchline of this paper is that the other three directions are all false. And I could put the same plot for attribution near 1,000. And so this kind of means that it's, if we start from just knowing the attribution, we can't conclude whether the feature is, or the model is kind of sensitive to changes in any sense. We aren't going to be able to conclude whether the model is kind of increasing or decreasing in this feature. And so this kind of is how I'm saying we should be understanding that this axiom is not holding for this specific set of methods under the assumptions. So, I mean, this took, 5 minutes or something to summarize the whole paper. The rest of this talk is going to be building up the mathematical structure in order to make these into precise statements and understand what exactly can we say, how do we prove it, what is left to do, basically. So let's start adding some mathematical structure. And by this, I'm just going to start, formally thinking of a model as just purely a function that takes my input space. So there's going to be, p dimensions. P is like the number of pixels here, to an output space. So we can think of this as an image classifier. It takes in images and gives me maybe a distribution on labels. Q is not going to be that important here. We can think of this as 1 if we'd like, outputting a probability or something. And P, we should just think of as the input dimension for kind of the rest of the talk. And then a feature attribution method, I'm always going to denote by this capital phi here. And this takes in 3 inputs. So one is going to be the model, the example X, and then mu here, which let me kind of walk through exactly what these inputs correspond to. So of course we have to take in a model. That's what we're trying to explain. And we're focusing on, feature attribution methods that take in a specific example and try and explain the model near that example, essentially. This is what saliency maps are doing. And so we can think of this as, some vision model and an image that we are trying to explain. Now, if all that I have is just this X value, this single example, I can't do that much beyond computing f of X or maybe gradients. I could do a full Taylor series approximation, I guess, but there's not much more I can go beyond that. And so interpretability methods or feature attribution methods also tend to define what has been called in the literature a baseline. And this is just a distribution over my input space. So this is the role of mu, to try and give me kind of some way to have some contrasting between what is my model doing at X and what is it doing elsewhere. And this is how feature attribution scores are computed. And then the output is just going to be a matrix in the number of input dimensions, technically by the number of output dimensions, but you can think of these as kind of saliency maps, one for each class that I'm trying to classify, something like this. And so you can kind of massage it into any, shape of matrix that you'd like so that you can overlay it as a heat map on your image. So just a couple classical examples. A lot of you have probably seen these methods a million times. And so I'm going to focus on 2 methods here that form kind of the basis of a class of interpretability methods, which is what we're going to prove results about in this paper. So SHAP is essentially a weighted average of the difference between including a feature from the actual input example and having that feature be sampled from kind of some ambient distribution, which is often the data distribution. And so this WS here is like a combinatorial weighting to try and account for how you swap features around. But it's basically like I have my specific input X, and I either keep the jth feature from that input or I do not. And all the rest of the features are coming from this kind of sampled X, which is usually from the data distribution. Integrated gradients is basically a kind of path integral from my actual example that I care about to some kind of representative capital X, which denotes kind of, again, an ambient distribution. It's pretty typical for integrated gradients. The kind of classical definition or our standard definition is for this baseline to be a point mass on something like the all black image, or maybe like the average pixel value for the images. But in principle, you can define it to be also the data distribution and average over these gradients. That just will be computationally expensive. Okay. And the specific structure of these two methods is not really going to matter. It's going to be properties that they satisfy, which then define a class of methods that satisfy those properties. And this class is what we're going to be able to prove results on based on those properties. So how do we go about kind of assessing the quality of such methods? Kind of common fallacy in the literature is how positive results are kind of interpreted as saying, I know what the truth is. I have a model that I actually understand quite well. And then I compute the attribution and I kind of say, yeah, that looks right. That kind of matches what my intuition was about the model. And this is kind of the backwards direction of what we would actually want to do in practice. Because in practice, the whole reason we're using these methods is because we don't understand the model well. And so what we actually need is the kind of reverse direction, which is where all I have is my attribution matrix. And then I'd like to know, what does F, F here being my model, do in a neighborhood around this example that I'm interested in explaining. So for example, what are some tasks where this matters? Well, looking back to the last talk in the seminary series, we can think about recourse. So in that paper, they have this kind of very nice description of what recourse is based on utility functions. And if one takes kind of the simplest utility function you can think of, you can imagine recourse is just like an optimization problem of, which direction can I move in to increase my F value? This could be if it's just, the probability of being in a certain class. Similarly, there's this task of spurious features, which looks at, does changing this feature actually change what the output of F is? This is kind of a classical task in feature attribution where it wants to know, is the model focusing on features that we think it shouldn't be focusing on? These are things that have correlations in the data, but no actual kind of connections to it's not going to generalize well. And so the way that we're going to formalize thinking about this, where we want to answer questions of this type, is I'm going to define two sets of models. So F0 and F1 here. For simplicity, we're going to think of them as being non-intersecting. And basically, this corresponds to me saying, does my model look more like the models in F0 or more like the models in F1? And so this is what I want to decide between. And this is essentially a classification problem, but we're framing it as kind of a hypothesis test, which I hope will become clear over the next slide or two. And so we can define a hypothesis test to just be a function that takes in my attribution matrix. So my hypothesis test takes in the saliency map, and it outputs some number between 0 and 1, which I should interpret as the probability that I'm going to conclude that my model looks more like F1. By convention, I'm just saying, a 1 corresponds to my model being in F1, a 0 corresponds to it being in F0. And you can think of the hypothesis test as kind of what you as a practitioner are implicitly doing when you look at a saliency map, right? You look at a saliency map and then you make some judgment call about what the model is doing. And that judgment call corresponds to you saying, I think the model looks more like X, or I think it looks more like Y. So why are we calling this a hypothesis test? Well, we can think of kind of the most basic hypothesis test that you learn on, the first day of Stat 101, which is, can we test for the mean of Gaussian random variables that we observe? So we have Gaussians with unknown mean, unknown variance, and I want to test whether the mean is 0 or strictly positive. Our interpretability method, stretching the word quite a bit here to talk about classical Gaussian testing, is going to sample some data from my underlying distribution, and it's going to compute a test statistic phi. And I've specifically using this lowercase phi here because this is the analog of what our capital phi, our feature attribution method, outputs. And we construct this phi in a very specific way so that when my F is in this F0, so in classical language, when the null hypothesis holds, then my phi follows some specific distribution. In this case, it's going to be a t distribution, asymptotically at least. And then I construct a hypothesis test by, I can think of it as just an indicator function for whether this phi is larger than some quantile of this known distribution that I have. And classically we would use, say, 95th quantile. So how do we then assess the quality of a hypothesis test in this classical setting? Well, we have basically two levers that we can play with. The first of these is the significance level. And so this says whenever the null hypothesis is true, so whenever the mean is actually equal to 0, then h here, again, this being basically when my h is 0, this means that I fail to reject the null. When my h is 1, I do reject the null. And so we sample a bunch of data from our ambient distribution, and we can average over my hypothesis test, but the indicator that I pick here. And so this just becomes a probability of me failing to reject the null under the case when the null is true. And we generally want this to be quite small. We want this to be smaller than some significance level alpha. And then we also have this lever, which is the power of the test. And this says when my alternative hypothesis is true, so now my mean is strictly positive, there usually has to be some kind of gap. We can't distinguish between mean 0 and mean 1 to the minus 10. So, we have some epsilon here. Then I'm going to now have, again, I sample some data, I average over my hypothesis test under this data. And now I want this to be large. I want to kind of reject the null in a sufficient number of times. So I want 1 minus beta to be close to 1. If you're kind of familiar with other language, significance level is just the probability of a type 1 error, and power is 1 minus the probability of a type 2 error. And so for the Gaussian means, usually we pick this alpha. So we define our hypothesis test based on alpha, basically. We can usually pick this to be 0.05, that's classical. And there's a kind of rule of thumb that if you pick n large enough, so remember n is how many data points I'm going to sample. This is a property of my interpretability method in this sense, that scales with the variance. So I have to understand, some bounds on the variance. And again, it's also going to scale based on what kind of mean differences I can differentiate here. But as long as I pick n sufficiently large, then, if it grows like this, you can generally be sure that your power will be at least like 80%. And so in this case, I've managed to get a small significance level in a large power. That's kind of a good test. So what's the analog in our setting here? We're going to have exactly measure our performance of this interpretability method using the analogs of significance level and power. And so first we have specificity, which is just 1 minus the significance level, except that these are now kind of, we don't have this sampling from data, right? Our interpretability method is just but we're kind of obfuscating that inside. Any kind of sampling we might do is going to be hidden in this phi here. And so this is just saying whenever the actual model that I'm observing comes from F0, so it comes from this class that I can think of as my kind of null class, then I would like my hypothesis test to output a 0. I want to get that correctly. But all my hypothesis test gets to see is this the output of my attribution method, which is this capital phi here. And so I would like this specificity to get as large as possible. So I always want this h to be near 0 when my f is in F0. And so this is just 1 minus the significance level, and sensitivity is exactly the power in this setting. And so it is just saying now when my f is in the other class, I want h to be large, right? I want that to be close to 1. And so the reason we move to these is because we want to maximize both specificity and sensitivity, whereas then you don't have to remember, am I minimizing this one? Am I maximizing it? We just want both of these things to be close to 1. And it's easy to maximize either one of them on our own. I could either set h to always be 0, just ignore the data and always conclude it's in F0. And now my specificity is 1. I always get it right when f is in F0. Similarly, I could set h to be always 1, and then I always get it right when f is in F1. If I instead pick h by just flipping a biased coin, so I ignore the output of my feature attribution method, I get specificity equal to 1 minus sensitivity. I get this trade-off. If I pick a fair coin, then it's 0.5, 0.5, but I can move anywhere I want along this line by just picking a biased coin. And so then the refined goal becomes, can we make specificity and sensitivity both larger than 0.5 at the same time, right? That's not going to be true with a biased coin, because if specificity is larger than 0.5, then, if sensitivity is, then specificity has to be smaller. And returning to the classical case, here the specificity is 95%, 1 minus this 0.05, and the sensitivity is 80%. So it has a 0.95 and a 0.8. Those are both, significantly larger than 0.5, 0.5. And so it's possible in the classical setting. We can then ask, is it possible in this setting that we're working in, where we're kind of using these methods to draw the same analog of conclusions from complex models? So, the spoiler alert is no. The answer is going to be no. That's our main theorem, basically. So let me first just list kind of the assumptions here in a very informal sense. And then later on, I'll go into each of these in more detail of how we can understand these assumptions. But basically, we need F0 and F1 to not be too simple. Otherwise, the task becomes kind of trivial. You aren't going to be able to prove impossibility results. And we need the input space to have some structure, which we're going to formalize as near the example I'm interested in. It's continuous. And I need my baseline to put some mass away from X. This is kind of satisfied for all methods I can think of. If mu is the data distribution, that's going to be true. Generally, mu is like, for integrated gradients, it's like a baseline on some kind of default image, which is like all black pixels or something. This is very far from my input example. And so generally, this is kind of trivially satisfied. And then for a class of feature attribution methods, which includes Shapley values and integrated gradients that I defined earlier, for any hypothesis test. So the idea is pick your method, satisfies, it kind of lives in this class. For however you want to construct your function H, your hypothesis test, you're going to have specificity less than or equal to 1 minus sensitivity. And remember, with equality, you can achieve by just flipping a bias coin. So what does this mean? It means that I've got no new actionable information about F, because any information that I had about whether F is in F0 or F1, I could have been just as accurate with this information for decisions I made by just ignoring what I observed for my feature attribution and flipping a coin. So tying this to, say, spurious features, if I want to get better at identifying when, say, my model doesn't actually depend on this feature, I necessarily have to get worse at identifying models that do depend on this feature. If I get better at one class, I have to be getting worse at identifying the other class. I can't somehow do well at identifying both of them. And so can we visualize this in maybe a kind of one more way to say it? Well, we can plot essentially ROC curves. So if you're familiar with ROC curves, what they do is on the x-axis, they plot the significance level. The y-axis plots the power. And you may have seen that there's kind of a diagonal line that lives along the middle here. And this is that random guessing line. This is if I flip a bias coin with different bias, I can live anywhere on this line. I can increase my or decrease my significance level, but I have to decrease my power. Or if I increase my power, then my significance level gets less and less interesting. So ideal methods live up in the top left here. These are things, this is like the Gaussian testing where my significance level was like 0.05 and my power was like 0.8. This is kind of an ideal method up here. And what our theorem says is that complete and linear methods have to live down here. They have to kind of live below this line. And so this is kind of the gap that we are proving, which is that, you can't overcome this. You can't move towards the ideal method that you would like, and you can't even live in this upper quadrant when your method satisfies these kind of common properties, which are, include SHAP, IG, and also some kind of common variants of them. Okay. So what are these actual assumptions that we have to make in order to prove this theorem? Well, first, let's think about the complexity of the input space. So if there's just one example X in my whole input, then I should just evaluate f of X and be done. Then I know exactly what my model does on this X, and there's nothing to interpret. Similarly, if there's only a handful, I'm also just going to do that. And there's not really much that we can say. So we're going to require that my input space has some ball around X. In this ball, my kind of space is continuous, my model is well defined, and I'm going to require that the baseline puts some non-zero mass outside of this ball. In general, this ball is going to be kind of the neighborhood that we want to understand what F is doing. So, as this shrinks towards being a point mass, gradients might tell you everything you need to know. As it gets larger and larger, now there's kind of, you're trying to understand the function more and more globally. And we aren't requiring any kind of restriction on the size of this ball, other than that it can't be so large that it also includes the baseline for the way that we're going to prove these results. Now, continuity here is not that important. Actually, this could be reasonably fixed by just taking a discretization of the space. But the algebra becomes a little more annoying because you have to kind of handle all the cases. And so it's easier to think of it continuously, which is what I just said. Okay, so the other kind of assumption we need is that our models are sufficiently complex. So it turns out if all of my models are linear, if I know that they're just, a times x, basically, then all I need to do is estimate this, slope or essentially this linear matrix that is defining my function. And gradients kind of successfully do this. And so it turns out that most of these methods will actually just recover this matrix. And then you know what the function is exactly. and there's not really anything to do. Then you just know your function. So if you know all your models are linear, I guess it's safe to use these methods essentially. Now, what F0 and F1 do is they're going to kind of describe the behavior of the model in the ball that I'd like to understand. So they're going to describe, how do I want to distinguish my model? Is it increasing or decreasing? Is it using this feature or not? This sort of thing. And so this is kind of fixed in terms of, what am I trying to understand about the model? And then what we need is that outside of the ball, they at least contain kind of all piecewise linear functions, in the sense that, like, outside the ball, I can define just a linear plane. So it's in 1D, it's like 3 piecewise. It's like, to the left of the neighborhood, in the neighborhood, and outside the neighborhood. And then you can build this into essentially like a hypercube on multiple dimensions. And then within the ball, they just agree with the kind of behavior that either F0 or F1 defines. For neural nets, this is satisfied. They already define piecewise linear functions. If you don't, linear seems like in some sense, it's a weak restriction. In some sense, it's strong, because we don't necessarily want our models to have this linear property. It can be relaxed to just assume that you can kind of hit all slopes of F outside the ball in some sense. But this would require, again, some more edge cases to handle. And so it's easier to state this for, I can include, piecewise linear functions in there. And so it is still possible that within the ball, I'm only interested in linear statements about my function. It just needs to have this kind of piecewise break, so that I can at least have it be linear with different slopes, essentially, inside and outside the ball. Because otherwise, it's just fully linear, and I can just estimate the slope matrix. And so then what are the methods that our theorem applies to? And I want to emphasize, these are not assumptions. These are things that you know what method you're going to use, and you can just check, does my method satisfy this or not? And so the first property is something called completeness, which just says that the sum of the individual feature attributions adds up to this specific thing, which is the output of F at that input, and then the average value of F under whatever my baseline distribution is. And the other property we need is that the method is linear, which people have used linear to mean a few things. I mean, linear is the most overloaded word in statistics, but here we're using it to mean that I have a bunch of univariate functions, and then I define a multivariate function by basically summing up the univariate function along each feature, along each axis. And then what this means is, if I have a function of this type, then my feature attribution for the jth feature is just equal to the feature attribution if I looked at just the univariate function. So if I take my multivariate function defined in this way and apply it to my feature attribution method, I get just the univariate feature attribution. So both Shapley values and IG satisfy these. And actually, it's not just that they satisfy them, they are defined to satisfy these things. These two properties are what motivates these methods as being, good methods in the literature. And kind of interestingly, these two properties are what allows us to prove the impossibility results. They're both why we use these methods, and also why these methods do not satisfy the results that we would like them to. Okay, so now I can state the main theorem a little bit more precisely. I'm going to state it in 1D, which then can be kind of bootstrapped into a multivariate statement. So let me fix kind of the example X to be arbitrary, the local distribution or the baseline mu to be arbitrary, and my feature also to be arbitrary. So I'm going to just kind of pick one example of this, one feature of this input X that I'm interested in. I'm going to fix some neighborhood, and I'm going to define two functions, G0 and G1, which are a little bit confusing, but I'm going to kind of walk through carefully what these mean on this slide and the next slide. And these are just functions that map from a little neighborhood around my X in one dimension to the reals, so to an output space. And I'm going to define my classes F0 and F1 in this univariate space as being all of the models, such that inside this neighborhood, they agree with this function G. And so my models can do kind of anything outside of it, but they have to agree with G inside the neighborhood. So this is a kind of strict restriction of my model space I might fully be considering. And so then I need some assumptions. So for the ball defined by this kind of radius delta, I need the richness assumption. So of course I need my input space to then basically be continuous in this ball. That was one of our assumptions. And then outside of the ball, I need to have all of these functions that are in F0. I need these to include the functions that have all the possible linear slopes when I get outside the ball. And so it could have more functions, but I at least need to realize these slopes. And then I'm going to let my feature attribution method be any method that satisfies completeness and linearity. And my hypothesis test is any function that takes in, here it's a real value because I'm just looking at the feature attribution for the jth feature, and it outputs something in 0, 1. And then I have the inf over my f being in the f1 class. So when it's in the case where my f's match g1, this is going to be smaller than the sup over f and f0. And of course, I want the right-hand side to be as close to 0 as possible, and the left-hand side to be as close to 1 as possible. And so this is an unfortunate tension to end up with, and it's equivalent to seeing that the specificity is less than or equal to 1 minus sensitivity. So this is exactly what we were talking about on the earlier slides. Okay, let me break down how these kind of G's come into play here precisely. So basically, is it restrictive to prove a theorem for kind of picking a G0 and a G1 inside a class like this? So we can think of, maybe G0 is the function, well, let's look at like specific examples of what G0 and G1 can kind of represent. So remember, spurious features is basically asking, does my model depend on this feature or not? Does it change when I change the feature? And so if I define my G0 to essentially be that the difference, like the function does not depend on this, I can think of f0 as being all functions f such that whenever xj is inside this neighborhood, it's exactly the same as if it was just equal to xj. So adding delta or subtracting delta does not change the output of my model at all. This is kind of my null hypothesis here. And so this corresponds to basically picking G's that exactly agree with the f that I'm interested in there. Whereas f1, I could say, well, let me pick a bunch of linear transformations that kind of give it some perturbation. So now it has some slope where this slope is non-zero. And when I change the jth feature, then it's basically some small linear perturbation. So if delta is small enough, this could capture kind of lots of cases, but it's also worth realizing that it doesn't have to be only functions that have a linear perturbation, right? It could also include lots of functions that have quadratic perturbations in the way that they depend on this feature. But I'm just saying one way to think about this is that it also includes these kind of small linear perturbations away from it. So this would be an example of an f0 and an f1 for the spurious features case. And for recourse, it's kind of the same idea as the spurious features example, where we can think of asking, again, this is like the simplest way that we could interpret recourse, which is just which direction do I move to increase or decrease my model? And this is saying, when I kind of move around in the neighborhood here, the slope depends positively on that feature, or when I move around in the neighborhood, the slope depends negatively on that feature. When I look at just the slice of my function through one dimension, which is all that we need for this theorem. And so basically, in general, I can write f0s and f1s as unions of these simpler sets. So I basically pick G's that kind of satisfy some properties I'm interested in. So if I'm interested in, understanding if my function is increasing or decreasing, I have a bunch of G's that are increasing, and I can union over all of these kind of simpler classes up here where they exactly match this G inside the small space. And I can do the same for f1. And if you remember from that statement on the previous slide, maybe I'll just go back to it for a second. Over here, we have an inf, and over here, we have a sup. So as I add classes to this just gets larger and this gets smaller. So this statement actually gets easier and easier to prove as I make f0 and f1 bigger. And so anytime that I'm interested in another G I want to test on, this just becomes an easier statement to prove, actually. And so when we can prove it for simple G's, then this implies that, but basically, if we were able to do it for kind of a general G that we're interested in, we would have to be able to also do it for some specific G. We would have to be able to distinguish between these. And what we prove is that B is false. We can kind of say, for any two G's that you pick, you're not going to be able to distinguish between them. You're not going to be able to distinguish between these two simple classes. And because of that, you also aren't going to be able to distinguish between the two more complex classes that are going to be much harder to define for your kind of maybe most general problem of interest you could think of. Okay, so how do we go about proving this type of statement? So I started this project actually trying to prove positive results about these types of methods. And then I realized I could make this picture, which I realize now is showing up super blurry, but hopefully you can still understand what this is showing. So basically, this is just looking at 1D models. So on the x-axis here, this is my input x. The y-axis is f of x. The shaded area is this kind of neighborhood I've been talking about in the theorems. And then this dotted line corresponds to the example I'm trying to explain. So in that case, it's x equals 0.1. And these feature attributions were all computed with SHAP, but it could have been done with any complete and linear method. And the basic idea is that kind of two implications. So the first is that just having the model behave differently does not imply that it will get different attribution. So all of the lines that have the same type, so for instance, all of the dotted lines, these all get Shapley value of 0 for this example. I think the mu I picked here is a uniform distribution, like an ambient baseline uniform. And so then you can see that this line is decreasing, this line's increasing, this line's totally flat, this line has some kind of quadratic curve going on. All of these get attribution 0. And so the interpretation here is that just because these have very different model behavior, they all kind of have to get condensed to the same attribution. So I can't say because these have very different model behavior, they necessarily get different attribution. And the reverse is also true, which is that the behavior being very similar does not imply similar attribution. So kind of the lines of the same color are all actually identical in the neighborhood, but they also have either Shapley value of 0 or Shapley value of 1, which on this scale is very far from each other. And so you can see that, for instance, this green line, it behaves identically in the neighborhood. So if I'm trying to understand something about, how does f of x depend on x near x, this is I would draw the same conclusion for the behavior, but one has Shapley value 0, one has Shapley value 1. And similarly for the blue line, the red line, and the orange line here. And so once you have these kind of two implications, you realize that basically whatever feature attribution you get, you're not going to be able to tell what is the model doing in this kind of local space. So how can we kind of bootstrap this up to the theorems we're actually stating? Well, how do we go about making these first, I guess? So the main takeaway is that in 1D, feature attribution is just a real number. It's just a scalar. And by completeness, I know that this feature attribution value has to satisfy f of x minus the mean. This is where we're using the completeness property of the method. And as long as I kind of give my functions at least some kind of flexibility. So here we're looking at 3 piecewise linear. In that plot, they were actually cubic, but I could have made the same plot with linear. It's just kind of pretty pictures have smooth functions. And I can fix any kind of feature attribution value that I want. I can use one of the parameters to specify what f of x is going to be, one of them to specify how the mean is going to change for f, and then the third parameter, I can make it do the function do whatever I want. So in that kind of quote of von Neumann, I can make the elephant wiggle its trunk. And so essentially, once I have even 3 parameters to play with, I can now make the function do whatever I want for whatever feature attribution value I'd like. So again, I was using cubics, but you can easily do this with piecewise linear functions. And then the way that you bootstrap this up to a multivariate function is you do this along each axis or each feature of your input, and then you can just sum them. And now you have a p-dimensional counterexample. And it's worth noting that in this p-dimensional counterexample, you can think of the inputs as all being independent. And a lot of the work in interpretability is on taking methods that exist, like SHAP or IG, and saying, well, they can fail when you have dependent features. And so we're going to add lots of bells and whistles to make them work better for dependent features. But these kind of theorems apply even when you have independent features. Indeed, that's how we can construct the counterexamples. So I could also construct counterexamples for dependent features. There's going to be more structure then. And so you're going to have kind of more complexity in the statements that you make. But in terms of adding more bells and whistles to handle dependent features does not resolve this simple issue, which is that even in 1D, it can't explain what the model is doing locally. And the kind of intuition for why this happens is that these methods are thought of as local, like they're given a specific input and want to explain what's going on near that input. But as I mentioned before, if it was really local, it would be something like gradient. But people have found lots of issues with gradients before. I'm not going to rehash those. And so then we added these baselines. But once we add a baseline, we now are not local at all, because actually now the attribution can depend on things the model does away from this example that I care about. And so I can either make the attribution arbitrary and have the model do things I don't want it to far away, or I can make the model be doing something specific far away, but the attribution kind of be fixed close by, but then locally it's doing something I don't want it to like. It's kind of, I think of it as like whack-a-mole, right? There's always some place popping up where things are happening that I'm unable to predict from just looking at this kind of simple representation that I have from feature attribution. So then how do we bootstrap these counterexamples into this hypothesis testing setup? So any hypothesis test H is only going to get to see the feature attribution value phi. Suppose that I have a feature attribution value phi that the hypothesis test assigns near 0, where the model is actually in F0, so it gets it right. I now have a recipe from the previous slide on how to find some model that is in the other class, such that I can give it the exact same feature attribution. Because H only depends on this feature attribution, that's going to give me the exact same hypothesis test. Now, this is kind of where the assumptions kick in. Why am I able to find this F1? Well, I have to be able to manipulate F outside of the kind of neighborhood. And so basically the idea here is that I can pick another F that exactly agrees with my original one locally, but as long as I can do kind of stuff outside of the neighborhood, I can make the feature attribution be identical and have kind of any different behavior that I want locally. And so then this lets me assign it to be an F1 based on the local behavior, but get identical feature attribution. And so this means my hypothesis test will have to also give this hypothesis near 0, and so it's going to get it incorrect. And I can do this in kind of any number of ways. I can kind of pick any pairs that I want, and so I can kind of scale this up to force you to always be making a mistake when you are getting something else correct. And this is, of course, symmetric also if I started from getting something in F1 correct. And so that's why we get this kind of symmetry between specificity less than 1 minus sensitivity and vice versa. So how important are these assumptions? Well, if F0 and F1 characterize X in a more restricted way, so they also tell me kind of something about how the function depends on X everywhere, then these assumptions might fail. But basically, if I specify what the mean is exactly, then phi can be used to learn essentially the mean of f of X. But it's going to do so no more efficiently than Monte Carlo. You're going to have to sample these functions, essentially. And so it's not clear how useful it is. If I'm only trying to distinguish between the mean of f, then I should just estimate the mean of f, and why am I using interpretability methods? And otherwise, I'm going to be able to construct the same counterexamples up to how different the mean of f is allowed to be, because that's where I get the wiggle room from, is that I can essentially manipulate my functions such that they get the same mean that forces them to get the same attribution, but they can behave differently. Okay, so I see that we are getting close to time, but basically a kind of obvious critique of this theory is that we're using imps and soups. We're requiring good performance for all f's in F0 and all in F1, and that's what we're proving is impossible. Now, I kind of tried to motivate this as not unprecedented because that's exactly what we can do with classical hypothesis testing. And because we're kind of using these in the same way that we use classical hypothesis tests, where we draw information and we say, okay, I feel confident that my model is in F0 or F1, I don't think it's actually an unreasonable thing to kind of strive towards, since we know that there are methods that can do this in other settings. But we really do only care about Fs that we see in practice. And so what if our F comes from running SGD on a very specific data source? Do these kind of results still apply? Because then maybe the counterexamples that we constructed are things that are not likely to show up from the data distribution. So how can we hypothesis test kind of real functions? Well, what we do is we pick very basic data sets. I mean, this is not a ML experimental paper. We are not picking LLMs here. And we basically learn multiple functions that have good training error using different seeds on these data sets. We kind of fix the train test split to be whatever the canonical one is in the literature, and then just retrain a bunch of times to good training error. And then for each of these functions f, I'm going to compute a ground truth. So I pick kind of tasks like the recourse, like spurious features, that can actually be just computed by evaluating f many times, right? I can kind of understand f at a very granular level, and then I know, does f increase or decrease? I know, is it sensitive to perturbations in this feature or not? I can just compute this. And then I can compute the feature attribution using existing libraries that exist for these kind of methods. And the way I conduct a hypothesis test is essentially the theorems are for any hypothesis test. Obviously, I can't show this experimentally because I can't experiment over all possible hypothesis tests. But I pick essentially what I think is the most reasonable, which is this kind of general wisdom that when my feature attribution is large, then the feature should be influencing what the model does. And when it's near 0, it should not be influencing it. And so the way that we do this is we say, well, we can pick some threshold. And when the feature attribution is larger than that, then okay, it should be increasing the model in some sense, or it should be decreasing the model if it's very negative below some threshold. And I can compute an empirical sensitivity and specificity, which is just an ROC curve, by varying these thresholds and redoing my test across all of these thresholds and seeing what does my curve show up as. So first we can look at kind of an easy tabular data set. So this is like classifying, I think this is like scores for how good wine is what this data set was. And we have a bunch of methods here. So we have Shapley values in red, integrated gradients with the two most common baselines in blues, and then some other methods, so like smooth grad, lime, and then just pure gradient. And remember, the ideal method lives in the top left. This has sensitivity near 0, and specificity is up near 1. And so ideally, you want your method to kind of follow this kind of almost go straight up and then straight across, where the lines are created by, or the dots are created by varying the threshold that you use for hypothesis test. And so what we see here is that, okay, so we have this integrated gradient line. This is, so the gray line is exactly the like random guessing line. This is what our kind of theory would suggest. And we see that for this kind of easy data, indeed the experiments, it doesn't live exactly on this line. Basically, there's kind of some juice happening here for the recourse question. But the methods that are doing best are things like gradient. Basically, this data is easy enough, things aren't saturating for these types of questions that you can just compute the gradient and know essentially the slope of the function in a non-infinitesimal neighborhood. For spurious features, this becomes much less clear. Basically, there's just more noise in the data for knowing whether something's actually depending on a feature or not, whether it's going to be sensitive. And so we find that essentially all of the methods live near this kind of random guessing line. We looked at this also for image classification. And at this point, it seems like basically once we're on the pixel stage, then it becomes very hard to answer questions of how does this pixel influence the model. We also looked at essentially like a concept stage. So it's like, first we trained a model to learn kind of, I guess, summaries of the pixels, right? Like intermediate structures. And so then there's fewer of these than there are a number of pixels. And then we can run the interpretability method on the second half of the model that takes these concepts as inputs. And we find the same results, that basically it lives along this random guessing line, even for these concepts that are kind of conceptually supposed to be useful for the model. And again, we see here that for these kind of tasks, even just like simple gradient is doing better than most of these methods. But gradient, it has its other problems. I could easily construct an experiment where gradient does the worst. This is not saying we should just use gradients, but it's more saying for these kind of simple tasks, we aren't, like, these methods are not improving on random guessing even, and they're not improving on gradient. And similar case for when we use MNIST. Okay, so one could ask, again, this kind of experiments are about average performance on the data, but can we prove theory about average performance? I guess, how do we even approach this? So one kind of statement is that, well, if my method is sampled from training on SGD, but this is going to require a pretty good understanding of how does SGD characterize the distribution over functions that I actually learned, which seems tough. And so we can pick a very toy case to understand, like, what could these theorems even possibly look like in this setting? So let me define my model class to be a bunch of polynomials, basically, of kind of a certain degree. I'm going to induce a distribution on this function class by just varying a coefficient of a Gaussian. This is kind of the easiest way to induce a distribution, is parameterize a model and then put scalar distributions on those parameters. And then I'm going to have my baseline distribution just have some kind of fixed mean. And then I can show that for any complete and linear feature attribution method, so the methods we've been talking about, the probability that the sign of my feature attribution agrees with the sign of the gradient is kind of bounded in this neighborhood here between 0.25 and 0.5. And for kind of certain tasks, including recourse or spurious features, knowing the sign of the feature attribution, so I can make this feature attribution be bounded away from 0, so it's kind of outside of a neighborhood, and then the sign is giving me some sense of, is this going to be increasing or decreasing? And I'm not going to be able to match what the gradient is doing. Even when my functions, these functions that I'm picking, they actually just agree with the gradient in this kind of neighborhood that I'm interested in. And so then essentially this says I'm not going to be able to answer these kind of questions correctly. And what that means is that there's at least, it's not quite the same as saying we can't do better than 0.5, 0.5, but it is saying there's at least a 25% chance that the function that you learn, the way that you interpret it will be incorrect in terms of your guess as to whether, is my method going to be increasing or decreasing when I move X in this direction. So this is a very toy example, but it gives a sense of how you would have to go about proving average results. Is you need to induce a distribution over the functions that you're interested in. So of course, an open problem here is, can we prove a similar result, but where pi is not this extremely contrived distribution I've picked, but it's, say, the distribution induced by training a model. And it is possible to prove similar results where you basically enforce constraints that my model has, say, 0 training error. This is not so bad, but 0 training error is actually not very restrictive at all, because there are lots of, if my neural network is high dimensional, there's lots of interpolating functions I can learn. And I mean, a massive part of ML theory right now is understanding what subset of these interpolating functions do gradient descent or SGD actually learn, and somehow why are they useful, right? So it's not enough to just say that the training error is 0. And then I'll try and end here on a very simple positive result that we prove and suggest an open problem for positivity. So in the experiments, I defined a ground truth by just evaluating my function many times, because these were simple tasks of just like, which direction should I move for f, or is my function sensitive to this feature change? And so for these very simple tasks, we can always do this. And here's a very toy example of how we can understand that. Essentially, we can apply sample complexity bounds to whether these kind of methods can understand this, which seems kind of obvious, but I haven't seen done that much in the interpretability literature. And so this is like very basic type of result from, the first course that you take on probability. But if I suppose that all my functions are L Lipschitz, and I'm interested in this task of knowing, does moving the feature increase the function by, more than epsilon, or change the function by more than epsilon, then I can come up with a very simple test which just kind of samples uniformly in my neighborhood, such that my specificity is always 1. So I always get the null case correct, which is that it doesn't change by more than epsilon. And my sensitivity is going to depend on how many times I sample that function. And so this is similar to the very classical Gaussian case I gave in as an example, where you can basically fix the specificity of your test, and then you just have to sample more. And this is how you increase your power, or sensitivity in this case. So it's a positive result because they can both be made arbitrarily close to 1, but this sample complexity is not that good. I mean, it's depending on epsilon and L and delta in kind of the most basic way you could imagine. So a kind of open problem here is, how can we get similar types of sample complexity results, which could be of the form, I compute feature attribution at many different examples and I aggregate them, I combine them in a certain way. And then I can use some additional structure about f in order to require fewer than this kind of exponential dependency on the number of samples I would need. Okay, so let me summarize very quickly. The punchline is that if all I know is the feature attribution, then I can't say with confidence how my function is going to change when I vary that feature. I can't answer local questions about how does f depend on this feature. This is basically an inherent consequence of the fact that feature attribution reduces me down to a very small number of real numbers that are defining my function. It's going to be basically, as soon as I have enough parameters, then I can make my function do whatever I want and get the same kind of representation in the feature attribution space. Existing positive results in papers are often of the form, I know this model and my feature attribution matches some sanity check for it. And this is backwards of what we would want to do in practice, which is I see feature attribution for an unknown model, and I'd like to kind of use it to draw conclusions. And so I posed a kind of open negative result, which is to prove similar things to what we did today, but for cases where my model comes from a specific training distribution, maybe on a specific data set, from a specific algorithm. And an open positive result is to discuss or prove results that if I aggregate feature attribution methods in a specific way, then I can get sample complexity results that improve on this kind of exponential dependence from just uniformly sampling my function and observing it at many spots. Okay, thanks again for listening and inviting me to the talk. And I know that we're kind of slightly over time, but I can take questions for a few minutes too.
Thanks, Blair, for the great talk. Yeah, maybe let's have a small round of applause for Blair. Yeah, so maybe if I can ask a very quick question regarding the experiments and how close some of these methods are to like random guessing like regarding what you find with respect to spurious correlation. Do you think that it gets worse when the models are much larger? That is, for small models, it's easy to be closer to like the optimal dot here, but not so when the models are much larger. What is your sense of what happens there?
Yeah, I think it's a combo of the model complexity. So, I mean, for this tabular data set, like you could fit very simple models. We fit neural nets, but you don't need to use neural nets. So presumably they're learning some like very kind of simple structure from the neural net. And so that makes it easier for sure, because then things just look closer to linear, or they look closer to this case where like everything is kind of moving in the same direction. And so then when your function behaves very similarly across a large neighborhood, then this is when feature attribution could actually be suggestive of what is going on beyond where you're looking at that point. And similarly, as your input space gets more complex, it just allows for when you zoom in on any spot, kind of anything could be happening at that local spot, even if globally you're understanding the function well.
Right. I was also wondering whether if we introduce additional assumptions like, let's say whether the model has a low curvature, for instance, locally, the Hessian is bounded by some constant. Do you think such assumptions might help in this case?
Yeah, so I guess I did mess around with this to see. I mean, that's kind of what the Lipschitz case is going
Yeah.
towards. And similarly, yeah, if you start adding these constraints with, say, like my model has to live in a certain space, or it can't be too curvy, then you can impose restrictions. I guess these all kind of boiled down to you can still come up with counterexamples for all of them. It just might be that you have to push things to, okay, now my distribution can be, it has to put mass in a few more places so that then I can make things wiggle in those spaces. And it wasn't super clear that, yeah, if I just impose like a Lipschitz bound or a lower bound on the Hessian, something like this, that I could get results that are meaningfully what I would want to see, like a meaningful positive results. And so I think that in some sense you need a lot of structure there. And so far, all I know how to show is that you would need more structure than is like what you would want to do. But I don't have a statement which is like, unless you have all that structure, you get that result. So there is some middle ground there that is not clear to me exactly where it falls.
I see. Okay. Are there any other questions from the audience?
I wanted to ask something. Thanks for the great talk. Would adding a restriction that the baseline is from the epsilon ball change the results? As you mentioned that you're assuming that the baseline is outside of the epsilon, right? And another thing is regarding a baseline, right, with the gradient. I'm not exact, like with Shapley values, there is the baseline, but with gradient, there isn't exactly a baseline. So I would assume that it's similar to maybe perturbations in a close epsilon, where epsilon is close to 0 or something like that. So your thoughts on this generally?
Yeah, so I guess two things. So one is that the method of strictly taking the gradient is not complete and linear. So it does not satisfy the like properties. So our theorems actually don't apply to gradient. But you can, prove very similar results about gradient by just showing that outside of any infinitesimal neighborhood, the function can be doing whatever you want, and gradient doesn't know what's happening there, right? But in terms of if your baseline is inside the epsilon ball, then it is going to limit the kind of statements that you can make, but it's only going to limit it kind of in the direction of that baseline, I guess. And so you can still have your function do things weird inside that epsilon neighborhood, but now it's going to be of a kind of more case by case statement. Or I guess what I didn't know was how to like properly characterize what my distribution is doing inside the epsilon ball in terms of how I would say the impossibility result. So if you gave me a distribution, I could then create the impossibility result, but I don't have a good way to say for distributions of this type, this is what the result looks like. For distributions of this type, this is what it looks like. So I have a very case by case understanding of it right now, but I think it would be interesting to try and characterize this more generally.
I think there's also a question from Tim.
Yeah, so I was wondering about, I guess it's more like a terminology question. So you draw this analogy with hypothesis testing, but then it's like formally not quite the same because you don't have a sample. I guess there's also a bit of an analogy with like data processing in information theory, like you like which information is still contained in phi. So it's just one, but that's also not, I'm not sure whether that's the perfect fit. So I was just wondering if, yeah, why you chose this analogy, or if you can say something about that.
Yeah, this is something that we, like, I went back and forth on quite a bit on how exactly we would characterize this, because you can just write it as a classifier essentially, and then try and say things using ML classifier kind of terminology for the descriptions. I guess the hypothesis testing analogy, so yeah, you can think of it as a hypothesis test is like you sample and then you draw, usually it's a 0-1 conclusion. And then if you average over that indicator, you get some number between 0 and 1. And so we're kind of zooming out to after you've averaged that indicator, and that's your kind of why my H lives in 0-1. But I agree that this is just an analogy. Like this shouldn't be viewed as an actual hypothesis test. And so the reason for framing it this way, I guess, is to emphasize how the literature uses it, similar to how they would use hypothesis tests in, trying to determine if, the mean of this distribution is 0. They use it a similar way, where they observe this and then they say, I have enough evidence to conclude that the mean is, this function is depending on this feature in some sense.
Yeah, thanks. It helps.
Are there any other questions? Okay, if not, then let's thank the speaker again. Thanks, Blair. This was a really amazing talk.